All right, so it is about that time. We're going to go ahead and get started. So this is week 7 of Code Foundry, and this week we're talking about API development and implementation. Also, what we're going to do this week is we're going to do a review of the content we talked about last week. Just because last week's meeting was cut a little bit short, it didn't have the greatest sound quality. A lot of people had a hard time connecting because I was in Mexico, so my internet connection wasn't the best. But without further ado, let's get into it. So, a little bit about Code Foundry. So let's give our itinerary for the day. Today we'll be talking about API development and implementation. We are going to recap over application architecture and development, which I think is crucial. We're also going to recap over what is an API, which we talked about in week 4. And then we're going to talk about API development and really dive into that. Lastly, we're going to have some project check-ins, get everything that we need off our chests. And then finally, there are 2 take-home videos this week. One is going to be that getting started with React Native video that I promised last week and didn't deliver. I apologize, guys. I was in Mexico and the tequila got the best of me, as it does to all of us. So I did get a little distracted and I forgot to post that video, but I'll be doing that on Tuesday. And then on Thursday, I'm going to post a video about developing APIs. I'm still on the fence about whether or not I want to make this having to do with developing an API with Express.js, which is a framework, or whether I want to capitalize on serverless APIs, which we'll talk about in this presentation. And I'd actually love to get y'all's opinion on that, what you want to learn more, whether you want to learn how to do serverless versus deployed server APIs. So we'll talk more about that in a sec. So what is Code Foundry? I know we have 1 or 2 new people on the chat today. It does seem like attendance has been dwindling. I'm going to reach out to people this week and see just where everybody's at, if anybody needs help, and if they still want to join us. But I'm really happy with the teams that I do have active and the people who are participating regularly. Thank y'all. I put a lot of effort into these presentations, so it makes me really feel really fulfilled to be able to present these to y'all and help in any way that I can. So a little bit about Code Foundry. We are orchestrated by Hispanic Hackers. Hispanic Hackers is a non-discriminating organization, but our goal is to democratize the tech industry for Latino and Hispanic people. So our priority is to be able to provide resources, community, and really just create organic growth within the Latino and Hispanic tech community. And so Code Foundry was a product of that. Essentially, we're a free tech bootcamp that gets entrepreneurs and developers in the same room working together and building products together. Our goal is to be able to train everybody at the same pace on how to build and deploy an application. And then the developers get their first projects under their belts, the entrepreneurs get their MVP built, and it's a win-win with a lot of opportunities coming out of that. This project is also hosted by Circle Square Labs and Capital Factory. Circle Square Labs is a full-service technology firm out of Austin, and the goal there is to build efficient and beautiful products. And what we do, I'm actually the senior software engineer for Circle Square Labs. We hire subcontractors to come on board our team and help us develop and deploy applications for clients. And we develop everything from APIs and backends to beautiful UIs, front ends, UX designs, etc. We'll even do graphics and marketing. And then Capital Factory is our wonderful host for in-person meetings. Our attendance was good enough this year, thank goodness, for us to be renewed with them in 2025. I just got the email about that. So that's a really exciting development because it means that we can continue our meetings starting next year in January, and then continue those out into the rest of the year when we have our second bootcamp cohort. So I'm really excited about that. I'm really trying to get as many tools and materials going as possible for the bootcamp. This is our first cohort, so we've been developing the presentations for the bootcamp and all of the actual action items. However, our next initiative with our second cohort is going to be developing customized take-home videos, because these take-home videos were largely third-party sourced, so we get them from YouTube and we find the right trainings that we want to provide, but we want to provide our own in-house, very, step-by-step, this is how you bring your product to fulfillment training videos. So that's going to be our next initiative. So we're really excited about that. And then that is essentially our operation here. We're really excited to bring you all these presentations and be able to help you along through your projects. So we're going to do a quick recap of last week's talk, and that was basically about application architecture and development. And so we basically talked about how there are three different platform bases, three different devices really that people operate on when they're looking at applications. They're working off of web, mobile, or desktop. Web technically isn't a device, but it's on the browser. It's cross-platform, so it works on any device with a browser. And it updates instantly with no installations required, meaning all you have to do is go to the URL and you can access it. Mobile applications, on the other hand, have to be specifically downloaded onto smartphones or tablets. There are native apps which are native to a specific platform, so those are built for either iOS or Android. And then there are hybrid apps which are built non-discriminately, which are platform agnostic, meaning that they can go on either iOS or Android, and those are built using JavaScript technology. They're usually wrapped in native containers and deployed onto native machines, but they use really non-discriminate code. So you can write JavaScript code and deploy it to both iOS and Android at the same time. And then finally, there are desktop applications, which are great because you can download the app and you don't always need online access to use it. There's a lot of direct interaction with hardware and file systems involved, and this is typically for more complicated software. So that is the idea behind our different platforms here. So this is a quick chart. We already discussed this. We're going to move forward pretty quick. But essentially, when it comes to web, mobile, and desktop, you want to use web for a very kind of non-discriminate application that can work on both mobile and desktop computers. Versus mobile, you want to work specifically on when you're building an app that you want to go on somebody's phone. The benefit of creating a mobile app is that it always exists on their phone, and every time they open up their phone screen, they see it. So they're more likely to use it in that way. Versus if you have a website, they might easily forget about it. Desktop, on the other hand, is installed locally on a computer. Those are typically bulkier apps and a little bit more difficult to build, but also have a lot of benefits in that they can be fully offline, have a lot of influence with the hardware, etc. So this is the chart we developed about our different programming languages. These are some of the key ones. There are some that aren't represented here, but these are the ones that you hear about most. You have C languages, which are shared between mobile and desktop development. You have Swift for Apple, Kotlin for Android, and then you have JavaScript and TypeScript and Java all being able to be used for mobile, web, and desktop. You have Golang, which is a primarily web development platform, but can also be used for desktop compiled applications. You have C# and Python, and then you also have your web development kit, which is HTML, CSS, Ruby for Ruby on Rails, and PHP. And then we abstract this into frameworks. When we're looking at frameworks, this beautiful graph, I'm really proud of these, basically shows you the way that these frameworks interact with these languages. And so you have React, which is cross-platform for mobile and web. You have Flutter, which is cross-platform for mobile and desktop. And then you have your web languages down here, your desktop languages here, and your mobile languages up here. And these are their frameworks corresponding on the sides. So we have Angular, Vue, Next.js, and React, which are the popular web front-end frameworks. But then you also have other frameworks for web development, such as Express, Java Spring, which is the Java backend framework for web development, Laravel for PHP, Ruby on Rails, etc. So I feel like this is a very helpful graph to have. Now, finally, we get into the most important part. And I find this part to be most informative because this is something that you can't develop applications without a knowledge of application architecture. Now, what a lot of developers do is they don't understand architecture, so they go into developing an application blind based off of YouTube tutorials, and that can turn into a very messy application. So having well graphed and and really well developed application is crucial of having the right architecture in mind. So the most common thought process when you think of a program is a monolithic program. These programs are typically like self-contained applications that don't really require many external resources except for maybe like external images or a couple external data points, etc. Maybe you're touching an API and bringing in data. But most of the code in this application is held on the machine. You don't really have an abstraction between backend and front end. It's pretty much all on one application. And you have all your dependencies and assets within that application for the most part, other than maybe some external assets. And so in this orchestration, we don't really have a distinction between front end and back end. Then we have the front end and back end application. This application is where we differentiate between our front end and our back end. The back end is typically hosted on a server or virtual machine. Meanwhile, the front end is on the user's machine. And what this gives you a benefit of is it hides all of the back end logic. So with front end applications, users can go in and try to access some of the front end files, dependencies, assets, etc. But if you have a front end back end model, you can essentially access your dependencies from the back end and then have these external dependencies which are hidden behind this layer, which is this wall right here between the server and the user's machine. Now, the beautiful thing about that is, say you're accessing a database. You don't want your database access to be in your front end. And the reason why is that if users can see the keys to those databases or see the code to access those databases, then they can easily steal the data that's being held and secure. So the goal is to be able to provide a backend which provides a security layer and allows you to access external resources in a safe and secure way without exposing that in the front end. Backends can also help with protecting backend logic and things that might be proprietary or more complicated. And it also has its own resources, right? So you basically abstract the amount of resources, and now you have resources that are separated for the server and separated resources used up by the user's machine. So say the application is really back-end heavy and there's a lot of logic that could weigh down a user's computer, especially if they're using like a Chromebook or something kind of tacky. Not tacky, but like less powerful, right? If you have a backend which is on a powerful server, you can access that with a really lightweight front end, which would allow them to have a really lightweight access from the user's machine with a really bulky server backing it up. So then you could have the server running, say, AI, while the front end only just has a display with the data shown, which is really lightweight and easy to download on any machine. Now we take this one step further by containerizing our application. So containerization essentially ties in the external dependencies and it creates this layer around it called a container. What a container does is it contains all of the dependencies and assets and resources within an environment that it can be run in very frequently and deployed to almost any platform. So the container already has everything that the program needs to run, and any platform that can run a container and has maybe Docker installed can run this. Most cloud architecture has the ability to run Docker containers. And most cloud architecture already runs in a containerized environment because it's effective for basically updating, switching out, and creating your resources and content. So containerization basically creates an environment for your application to live on without it having to exist on the server. This also allows the application to coexist with other applications on the same server because each one can be allocated resources and already is packaged with its external dependencies, so it doesn't need a lot of TLC. So you could run multiple of these backends on one server if they're containerized because you just spin up the containers. Also, please feel free to stop me if you guys have any questions. I'm running through this pretty fast, but this is a very important step because we're talking now about cloud architecture and how we're going to deploy our applications. Again, if you're going to deploy to a server that you're not managing yourself, so like a server like AWS or Google Cloud, you're going to want to containerize your application. And it's a really simple process to containerize, but that's something that we'll get to, I think, in week 10. So microservice takes containerized applications one step further, where all of our parts of our application are all containerized. And what this does is it allows us to be able to separate and really package, compartmentalize how our application works. So say you have a container which is specifically for user data, which would be vetting and retrieving user data and returning it to the front end. And then say you have another container which is in keeping the logic for the application. These two containers can interact with each other, and say we need to update the backend logic, we can update the backend logic without having to provide a whole update to our whole application or to our user data container, right? All we have to do is switch out this backend container, and then we don't have to worry about the other container. And so the nice thing about containerization and microservice applications is that you can switch out your code really easily because you just have to switch one container instead of having to switch out and update the whole application. Another benefit of containerized applications is that you can use the same container for multiple applications or multiple purposes. So say you have that same user database retrieving container, you could use that in this project, but you could also use that same container in another project that uses the same technology by just hooking it up with an API in between. And these lines in between the different containers are representing requests. So if we go all the ways back to our front end back end model, we're making requests here between our front end and our back end, which is set up using an API, which is what we're talking about today. Meanwhile, with microservice, you're making requests between your services, and setting up an API can be very, very simple, which we'll see today. Finally, our last model is serverless. Serverless is exceptionally important and very interesting. It takes our containerization one step further, where our cloud provider already has the ability to containerize our code for us without us containerizing it and deploying it ourselves. So all we do is we provide our code in the form of functions, which get containerized or wrapped with all of the resources it needs to run. So say you want to deploy a Python program, a Python script that can be easily accessed. What we do is we go onto AWS Lambda, for example, and we input our Python script into a function. And that function wraps it in a Python container that can run Python. And it deploys that to a server and waits for us to access it using an API gateway, such as this one here, which we see here. Now, when a user wants to access our function, what it's going to do is it's going to access the gateway, which is our API rules for accessing our function and our backend logic. And then it's going to balance out our load, meaning that it's going to distribute the number of requests it gets to the appropriate functions. And this is usually done in the gateway app as well. And then it's going to go ahead and send our request to the appropriate function. Now, a function will go ahead and it has the ability to access assets. For example, in AWS, that would be accessing media assets, such as media that's contained in the S3 service, which is just its simple storage service. which kind of acts like Google Drive. You can update any kind of media, upload any kind of media to it. You can also access other external resources, which might be other containers, other functions, databases, etc. And so the beautiful thing about this is that AWS, or our cloud provider, basically containerizes everything for us, and then we don't have to mess with it. All we have to do is provide the right code to access it. So we don't have to worry about deploying or containerization in this case. We just have to send it our code and upload our code. Now, one last thing that I wanted to mention is that in a microservice environment, these external containerized resources could just be a database. In a lot of containerized applications, one of the containers would be the database, and that would contain all of the user's data, and it's wrapped in this container, which makes it more secure and provides an additional layer that can be kept alive. So if we're trying to update our application, we don't update this container with the database in it, but instead update the other parts of the application, which saves our database in the long run. So there are microservice and serverless solutions for everything. Say you want a database. You can either create your own database and containerize it yourself and then deploy that container onto cloud hardware. Or you could just go to the serverless route and hook up gateway to an external resource, which could be DynamoDB or one of AWS's resources. And in that way, you're creating an API that can go ahead and access the resources in that database. So that's really great too. And in that way, we don't have to package our own database. Databases are already packaged. So that's the concept of a service that's provided by these cloud providers. A lot of times it's just code or infrastructure that has already been containerized or packaged for us with a pretty bow or ribbon on it that we don't really have to mess with. And we'll talk more about that when we get to cloud deployment, which will be, I think, week 11. So the last thing we talked about last Monday was what is React Native. What React Native is it's a framework for building mobile applications using React and JavaScript. It was developed by Facebook, and it enables us to create cross-platform apps for iOS and Android. React Native is really easily exchangeable with JavaScript. With React.js, it's just React.js uses web browser components such as divs, headings, and paragraphs, while React Native uses native components like buttons and views and different objects like that. So React Native has a lot of the same features as React.js. It has reusable components, so you're using a component structure. It has hot reloading, which allows you to instantly update your app when you're developing by just saving the code. It has native modules, so it will allow you to access native properties of your device, such as your GPS, your camera, etc. It is JavaScript powered, which makes it really lightweight and easy to build with. And then there's a lot of third-party plugins that create an extensive community. So we're not going to get into React Native versus native development right now because we talked about that last week. But this is a quick recap. If you're watching the video, which thing to note is that I didn't record the video for last Monday. So this Monday will be a recap of what we talked about last Monday. So if you're rewatching this video, you can go ahead and pause and look at this table in more detail. React Native components look a lot like this. Instead of using divs, we're using views. Instead of using paragraphs, we're using text. And these React components are coming from our React Native library. And we have a question from Ruth. In what type of projects or situation would it be ideal to use a serverless versus microservice approach? Okay, so that's a really good question. I'll go back and answer that right now while we're pretty fresh on the subject. And then we'll go back to React real quick. So essentially, microservice applications would typically be used for more complex applications, very complex applications, I would actually say. And the reason why I say very complex is that they're used for applications where you have lots of working parts, and you might need to swap out one of the working parts without swapping out the whole entire backend. So in that case, it could be, for example, user logic paired up with as well a database, which could also be paired up with a app logic or game logic even, so it's a more complicated structure, and you want to be able to create this so that you can interchange the different parts of the application without having to mess with the rest. This is also a great practice when you're planning to have a really big company, where you're planning, for example, in Facebook, you want a department that works on the Facebook Meta Ads platform part, and then you also have a department that works on the Meta posting part, right? So Meta is a great example for this, actually, because they use a lot of microservices. Instagram and Facebook are both very similar apps. So there are departments in both of those applications that will share code through containers with each other, because they'll share the containers with each other without having to duplicate the same code over and over again for each code base. Similarly, Meta would have, say, want to update its Meta Ads container without affecting the rest of the app. And so by using containerization, they can do that. They could also stick specific teams on one container or one part of the application. And the teams, yes, have to coordinate how those parts of the application work together. But other than that, they're very focused on the internal parts of their code. So microservice applications are used for segmented code or compartmentalized code that's potentially more complicated than a serverless or a front-end back-end application. Meanwhile, serverless applications are used for really simple apps, such as, say, all you have to do is access data from a database, and you don't want to create a whole back-end for that. Because as we were mentioning, these back-ends, even if it's containerized, will be running on the server almost 24/7, and they'll just be waiting for somebody to access them. So in the case of serverless, these functions get booted up whenever somebody wants to access something, and these functions are so lightweight that it's quick boot up times. And the hardware that these functions are stored on is optimized for these functions. And AWS or Google or Azure, they provide the infrastructure for you without you having to manipulate it. So the nice thing about serverless is that you really don't have to touch it much. You just have to set the configuration profile and let it be. So I would recommend a serverless app if all you need is like tracking user usage. Say you have accounts, and say you want to access a database and pull data from there without having all of that exposed on the front end. This is a really simple solution for doing so. Other properties of serverless applications, there's a lot of granularity, and you can implement a lot of security features that are built into AWS or your cloud provider. And so if you need something that's really secure and kind of locked tight, and you want very specific user groups, and you want to have an easy interface to edit on, serverless is also a good idea too. The other benefit is that serverless provides you with dashboards, because you're doing all of this online typically on like AWS's website. So you already have the dashboard for going in and editing things. Versus if you're creating a microservice application, all of your API content goes in code format. So you have to code everything in instead of having this kind of already built-in interface for just dragging and dropping the code, copy pasting the code that you want to run. I hope that makes sense. Let me know if y'all have any other questions. But I'm going to move back to React. Oh, Ruth is typing. Yeah, let me know if you have any other questions. I'm happy to answer. No problem. These are really important concepts to understand. So, one last thing to mention is that you can have a serverless app which runs containers, which are microserviced. So for example, I know the Ion project is working with creating AI children's books. And those AI program, the AI portion of that program is probably going to be containerized somewhere. And what you can do is you can deploy that container as an external resource. So you can deploy that container to AWS. And again, we'll talk about that more when we talk about cloud deployment. But you can deploy that container to AWS and use it and access it as an external resource from one of your functions. So say the only purpose of your function is to vet out user access, because say you want to make sure that the right user is trying to access the right thing. But then you want, after that user access has been authorized, for it to access our AI container. You can do that easily using a serverless model or a hybrid model where you have serverless components, but you also have microservices that you've built out yourself. That's the beauty of cloud infrastructure these days. And it can be really complicated. There's definitely a learning curve to it. But y'all are taking this step by step, and I think y'all are really learning and improving, especially when I see your projects. It's pretty cool. So React Native components are using native-like components instead of HTML components. That's the basic concept. I'm not going to get into this example a ton, but basically our styles are created using style sheet and using JavaScript instead of CSS. Here we're using React Native libraries. So our React Native libraries allow us to implement navigation, global context for our app. So this is managing global states. Axios or Fetch for making API requests, since technically our APIs, our code is written in JavaScript, but it's not run like the browser. So we can't make API requests like in a browser. We have to use a library for making our API requests. Lottie is great for adding animations. There's a couple other libraries for creating UIs and managing the workflow. And these are other popular ones. So React Native use, we typically use React Native when we're building cross-platform apps, prototypes and MVPs, consumer-focused apps. Really, anytime you want your application to go on a mobile device, but don't care if it's specifically Android or iOS. And so that's when you would use React Native. So lastly, before we take a quick water break, we're going to recap on what is an API. We talked about this in week 4, where we were basically discussing the basic principles of web, and now we're moving. We've already moved past web, and we're building out apps now, which is pretty cool. So an API is basically a set of rules and software that allows two different programs to talk to each other. This can be a set of rules between, say, like an embedded systems application and a online server, but typically it's between two servers, right? And so, or to a server and a client, right? And so how does it work? APIs act as messengers, relaying requests, which are requests made to ask for certain data, and returning responses. Our common uses are data access, such as, for example, loading up Google Maps or maybe the weather. Services integration, so integrating two applications together, or automating tasks that could be repetitive, creating workflows, etc. So this is our graph of how the internet works. We've talked about this a couple times. Essentially, our computer makes a request, which goes to our internet service provider network through our router. That will go ahead and go through a bunch of satellite or fiber optic networks, usually fiber optic undersea cables, and those will get routed by data centers. That's why big data centers are like very profitable, because they're not only holding data, but they're also routing data to other locations. Then that data will get sent to a domain name server, which will direct our request to where our actual host server is located based off of the domain name. And then we're going to go ahead and ping our host server, which will have the code that we want to either run or return data or return code. And that'll go all the ways back through this network back to our computer. So some integration terms, we have request, which is that initial request for data or whatever we're actually asking for. We'll have a response, which is the return data, and that's usually in JSON or XML format, and we'll talk about that a little bit today. We have asynchronous requests, which are triggered outside of the normal code loop, right? So the code loop is constantly running, and we might have multiple loops running at one time, but these asynchronous requests will execute without affecting the whole loop's running, meaning it won't interrupt other processes. So say you make multiple requests at once, all those requests will go off at once and they won't affect or interrupt each other. And then finally, we have data handling such as parsing, which basically means taking our data returned, and turning it into a format that our application can read. So here's an example of our API. We're not going to get too far into this, but this is using JavaScript to ping our API, where we're using the await keyword and the fetch function. But it's going to work a little bit different in React Native since we're using libraries like Axios to actually make that request. So instead of using browser built-in functions like fetch, we're going to be using libraries to help us fetch our data. So before we get into the meat and potatoes of this lesson, we're going to take a quick water break. We will meet back up at 7:52. So feel free to type any questions or requests or comments you have in the chat, and I'll answer them when we get back. Okay, we're gonna hop back into it, talking about API development. So this is the real meat and potatoes of our talk, and yeah, let's get to it. So when it comes to API development, there are a couple languages that we use to develop. These include Express.js, Java Spring, Laravel. Actually, Laravel might be a front end. This I'm on the fence about. Ruby on Rails is a backend though. .NET is also VB.NET is also a backend, and so is Django and Flask. Now, each of these kind of uses a different programming language. For example, Java Spring uses Java, Django and Flask use Python, Express uses JavaScript. But the key fundamental is that these are all back-end web development languages, meaning that they don't really support any front-end components or libraries, etc. You can still return front-end data. For example, if you want to return a web page, you can do that. It's just it doesn't support a lot of use of, say, components or properties, etc., like our front-end frameworks do up here, which are Angular, Vue, Next.js, and React. Another thing to mention is that these front-end frameworks can also be used to develop an API. However, you'd be wasting a lot of their abilities, and because they're more complicated in order to be able to provide all of those front-end solutions. So front-end specific frameworks can still be used to create a back-end web app. However, you'd be basically overcomplicating the situation. Back-end web apps can still be used to return front-end data, but it's not going to be as sophisticated as these front-end web frameworks. So that's why these web frameworks specifically are used for building APIs. There are a couple different types of API. There are open APIs, which are publicly available and usually given by third parties, such as Google Maps. A lot of these APIs require that you maybe register for a key, which provides some limited amount of use, but they aren't really discriminating, so anybody could ask for access. Meanwhile, internal APIs are private. The idea behind internal APIs is that they're used to coordinate between two private systems. For example, if we had an HR system and we had a payroll system, we would basically send data between them, and we want that to be private and only used by our company. There are partner APIs, which are APIs given by other companies that partner with a different company, right? So an example of that would be PayPal API on an e-commerce platform, where that e-commerce platform is partnering with PayPal to use PayPal's integration services. We have composite APIs as well, which is the last type, and that combines multiple APIs and services into one single API. So essentially, say we want data that encompasses weather and location and other components. This composite API will take from multiple APIs, and all we have to do is ask it a single request, and it will find the right API to access. So it's basically combining a lot of APIs into one. One really interesting composite API idea I've had, and I see to be have a lot of potential, is a composite AI API. We access AI models through APIs, and a lot of times those AI models are run on servers that we access through APIs. So if you could bundle, say, ChatGPT with also Google's Bard, right? I think it's still called Bard, if not whatever they changed their name to. But if you could package all of those together, that would be really cool as a composite API. So some key API concepts. You have your endpoints, which are the specific API URLs where the API can be accessed. You have your middleware, which are functions that are run during the request response cycle. And these execute before requests reach your intended route. So in terms of API, we access an API at a specific route. The route meaning the the terms that we give it to the path that we give it to get to the destination we want. So an API is typically composed of multiple routes. There could be a route for a specific image. There could be a route for some specific data. A route is basically just the path that we have to take in order to get to the right location. And that is basically given in the form of a URL. And so that URL, you know how you'll get on a website and you'll have www.website.com/about. That /about is the route. Or if you went to /team, that /team is also a route. And so middleware, what it does is it runs a function before heading to the route. A lot of times this middleware is used for authentication, such as verifying user credentials. So before we even send a request to where it needs to go, we check to make sure that the user is verified and authenticated. Another example is logging middleware, which will go ahead and before it sends it where it needs to go, it'll log it so that if it receives an error or another issue, it will log where that error was going to, which is really helpful. So middleware is basically triggered before we reach our route, and it allows us to do things like authentication and logging. Hooks are another key API concept, and they allow the clients to subscribe to specific events or triggers. For example, we can subscribe to payment being processed and then send data to a client when that happens. So basically what this means is that we will go ahead and wait for a specific action to happen. And when that action happens, we'll usually go ahead and make a request to yet another API. So that can be really helpful when you're, say, trying to respond with data, but your server is going to take a long time. Event hooks are similar, except they validate before processing. So like they trigger specific logic based on the lifecycle events in the API. So you can have your lifecycle events defined and then trigger them accordingly. There are another key component to APIs are the HTTP methods. So when we make a request, we typically specify the method we're using to make that request. And there are a couple different methods that provide a standard for what we're asking. There is get. Get asks to retrieve data from a server. Hey, Alex, it seems like you're... Oh, you got it. Cool. So get retrieves data from a server. And typically the get action is a read-only action. It doesn't modify the data, and the parameters are often sent as part of the URL as a query. Post, on the other hand, sends data to the server to create a new resource. It will create a duplicate resource if a matching record exists, and it's often used for adding new entries to a database. Put is used to update a current existing resource or create one if it doesn't exist. And if no matching record exists, put will create a new record. So these are guidelines, or HTTP methods. There's a couple other ones that we'll get into in a sec, but these are guidelines. They're not something that's already built in when you program an API. You have to program it yourself. But the guideline is when you receive a GET request, you should be only modifying or only reading the data and not modifying it. And you should be receiving parameters sent as a query string. So these are the guidelines for creating a API with these request different methods that will be specified when we make our request. So we'll say, let's get this info. And in our query, what we'll do is we'll say, let's provide a user ID and we'll get their info from the database. So what we'll do when we receive a get method is we will go ahead and check our database using the query ID that we have been given for the user's data, and then we will return it, but we won't modify the data, right? And so all of that logic has to be programmed, but this is essentially what get methods typically do. The last couple are patch. Patch will partially update an existing resource. It modifies only specified fields, and if no matching record exists, it doesn't typically create new records unless that's specified for it to do so. And then we have delete. Delete will remove a resource from the server. For example, deleting a user account. This is irreversible. And then there are other options like head, which will allow us to retrieve headers, options which will allow us to determine allowed HTTP methods, and other content. We'll talk a little bit about cores a little bit later, and trace, which is a debugging tool. So next we have status codes. Status codes are returned by a response after we've done our internal processing. And these status codes tell the client who has requested the information what is going on, right? Like, what's the deal? Because maybe you return information that you weren't expecting. If you don't provide a status code, you don't really have any context for why the right information didn't get returned. So these status codes give us context for why we're receiving the data we're receiving. 100 is a status code used for continuing. This 100 through 199 are typically informational, so they're not very helpful, other than they tell us what's going on with the server currently. Success tells us whether or not, or it tells us that our content was successfully created or received or understood. So if we get the 200 response, that's the one we want. It means all was good, server is returning the requested data or whatever it's supposed to be doing. If we get 201, it means all good, we created the right resource, and the resource was created. And if we return 204, it means no content, but it was still successful. So we're not returning any content, but it was still good. And again, all of these codes have to be programmed in and returned very deliberately. They're not something that's built in when you build an API. You have to specify that these codes get returned so that on the back end, say you run into an error, you can send a client error or server error response, right? So these status codes give you context. Redirection is typically the 300s. For example, moving a resource that's been moved, or a resource that is found but temporarily moved, one that's not modified. 400s are really interesting because they're client errors. It means that the API that you are requesting to, you gave it the wrong information, right? So like, say you make a request, but you give it the wrong API key. You might get a bad request returned. Or say you give it a user ID that doesn't exist. It might give you a bad request saying, look, you made a request and we don't get it. We can't, or a 404, you might get it not found because the resource was not found, right? Because that's the server saying, look, we tried looking for this user ID and it didn't exist. And so the 404 error should be returned when we can't find it, our resource in our backend logic. Lastly, we have server errors, which are our 500 errors. This is when, instead of it being an issue with what the client sent or the request had in it, this is an issue with how our server was processing. So say you run into a bug in your code and AWS shuts down. You can return an internal server error indicating that, hey, this isn't an issue with the user trying to send data. This is an issue with the server trying to respond with data. So finally, when we're talking about APIs, there are a couple different protocols. Again, APIs are pretty much the rules on which our application can communicate with other applications. So when we're talking about API, these are all guidelines. And one thing about APIs is that there are API protocols, which are kind of like frameworks, right? They're rules and processes for putting these APIs into place. The most common API type is representational state transfer, or RESTful APIs. These are really great for simple stateless applications. such as CRUD, which is create something, update, or delete. What's the R? I don't know. Return, response, something like that.
I think it's read.
Read? Ah, yeah, that makes sense. Read. Yes. Creating, reading data. So creating new data, reading data that already exists, updating data, or deleting data, right? So REST is used a lot when we're building applications that are simple and we're just trying to create applications that can access a database more or less. You have stateless communication, which means that it's not cached. So you don't have like state that's existing on the API's end. It's just, you're just sending a request. You have client server separation. Resources are based, it's resource based, so you use URLs to access your resources, and you use common HTTP methods like get, post, put, and delete. Our data is usually returned in JSON format. SOAP, on the other hand, has more strict standards, built-in error handling, and former contracts. So I think that this one is something that you have to actually license. It's used more in enterprise applications where the priority is security, transaction reliability, etc. GraphQL is a newer API protocol. I think this one was created by Facebook, I want to say, Meta. It's ideal for applications that need to fetch complex data structures, such as social networks, where you're basically, again, looking at like a huge graph of data instead of maybe something that's just tabular or basic. You have a single endpoint for all requests. You are allowing clients to specify the shape of the response, and you have a flexible and efficient setup for complex data requirements. So again, you can the client can actually specify, I want this data specifically with GraphQL, and that's pretty interesting. But it's also more complex and more heavy duty. So a lot of times it's used for complex applications and not so much for simple ones. And then finally, we have WebSocket, which is for real-time communication. This is for live streaming, like messaging systems or live updates. And so this is suitable for like chat apps, gaming, or live notifications. So we're going to talk about RESTful API concepts because I don't think that y'all will be needing these other API types as much as you need a RESTful API for your projects. So when we're talking about RESTful APIs, we're talking about statelessness, meaning that the client, the server isn't keeping track of what it's sending back and forth. All it's doing is fulfilling the requests one by one, but it's not storing anything or caching anything about previous requests. Other than unless something explicitly indicates that it wants to be cached, right? And then we can keep like a log file and keep some info about that. Client server separation. So we have two different entities. We're not trying to stream inside of an application, but instead we're trying to connect from outside of the application. Cacheability, so explicitly indicating whether they are cacheable or not, and this helps improve performance. Uniform interfacing, so a consistent interface that simplifies interaction between clients and servers. That means that you have standards and that you are providing this whole HTTP method based getting, putting, etc. Format. And then JSON formatted, so it provides the ability for lightweight, human readable object type data. Now, some API development tools are Postman or Insomnia. These are used for building and testing our APIs. And what these tools allow us to do is they allow us to try to access our API at different endpoints and see what comes out as a response when we're programming. So that's really nice because when we're creating our application, when we save our application, our API, we can go ahead and test with a Postman or Insomnia, and we can basically say, try to access this URL or this location with it. Meanwhile, Swagger or OpenAPI are a specification for describing RESTful APIs, and it provides a structured way to document your API. And there are some documentation tools for these API standards with Postman and Insomnia, which is really cool because it can go ahead and document it for yourself. So something really important to note. Writing effective documentation ensures developers can easily understand and how to interact with the API and provides example requests, responses, and authentication methods. What this means is that it is crucial that you document your application and your API. And it's crucial to do so because if you don't, if you have a new developer join the team, they're not going to know how your API works. They're not going to know what tries to access what and what credentials it needs to have. They're going to have to go through all of your code to figure that out. And say you hired a really bad programmer to develop it, or you yourself didn't develop it very well, then it's going to be even harder and create a lot of tech debt. So creating effective API documentation is exceptionally important. And you can find standards for documenting your API with Swagger or OpenAPI standards specifications. So we have API authentication. That's another portion of APIs. This is basically used during middleware steps, like we were talking about with middleware. What middleware will do is before we actually go and route to our resource, we will go ahead and check to make sure that our requesting user is authenticated appropriately. So these are the most important API authentication tools. There's OAuth 2, which is used for authorization. It's a framework that allows third-party applications to access user data without sharing credentials. You have API keys, which are really simple credentials for APIs, and that's just providing like a kind of a password, right? And what that password does is it says, okay, this application has access to the right of passage to access another application. And then you have JSON Web Tokens, which are token formatted ways to securely transmit information. And so these are like keys that help you access the data that you need to access. So the most important part here is securing API endpoints. And so some basics for that is using HTTPS, which we talked about in week 4. What that means is we purchase an SSL certificate, which is a secure socket layer certificate. And what HTTPS does is rather than using HTTP, which is the hypertext transfer protocol, we use the secure socket layer version of that, which encrypts the data going between the client and server. Also important is implementing roles-based access control, which is RBAC. And that determines user groups it basically determines what users can access what. So you are creating roles or user groups which specify you are allowed to access this resource, but you're not allowed to access this one. And lastly, protecting sensitive endpoints with additional security measures, such as API keys or OAuth 2, is really important as well. Last thing about authentication is CORS. CORS is a headache. Let me tell you, CORS is annoying, but it's important. What CORS does is it determines what websites or what clients can access what server materials. So you can specify and say only requests coming in from www.hispanichackers.org can access this API content. And so the key thing there is that we are specifying that it has to come from Hispanic Hackers and it can't come from any other website or application or browser, right? Not browser, but page. And so what we do, the way it works is when a web page makes a request to a different domain, such as an API, the browser sends a pre-flight request, which is our options method, to check if the cross-origin request is allowed. If it is allowed, it'll respond with the appropriate CORS header to tell the browser whether it is allowed or not. So we have access control allow origin, access control allow methods, access control allow headers. Access control allow methods tells us which methods can be used. Allow headers tells us which headers can be used. For example, a lot of times our API keys are specified in the HTTP headers. They almost exclusively are. And then allow origin tells us which domains can access this resource. So which origin point. And an important thing here is using the star tells you all, basically. That's the symbol for everything. So when we're creating an API, we want to prevent abuse of it, because a lot of times, say you publicize an API that gives access to the weather. That means anybody or everybody could access that API. And if you have a programmer who's a really bad programmer, they might program their application so that every time the smallest thing updates, they'll try to ask for more data from the source. So that means that they're constantly pinging your API, which is creating a huge amount of traffic and will cost you money on infrastructure costs. So we want to basically make sure that our API doesn't get overused or abused by a single user or multiple users. And so what we do is we provide rate limiting and throttling, which will basically determine the number of requests a client can make within a specific time window. And throttling determines the rate at which they can actually make it. So some implementations, you typically have a token bucket. There are a couple different types. There's having a token bucket, which is allowing you to have a burst of traffic, but with a maximum number of requests per time period. So you basically have a ceiling. A leaky bucket will spread out the requests evenly to prevent surges, and then a fixed window limits the number of requests in a fixed time window. So that is specifically for your rate. And so what we do is we implement this in middleware, such as the express rate limit package, which we can load into Node.js. So say we're building a Express.js backend API, we can implement that using express rate limit. And so we use middleware to typically rate limit and throttle our APIs. So this crazy structure is the typical API structure for your application. I really like providing these, what the directory is supposed to look like for every application, because this helps developers and engineers know how should I be structuring my application so that other people can easily access and understand it. And so here we have our source file. This is an Express.js API using the Express.js framework. That's why we have our Node.js, which is the runtime that Express.js uses. We have public, which is our public assets, such as images or static files. We have our source folder, which have controllers, models, routes, middleware, configs, utils, and our entry point. So the way that this is structured is we have our entry point, which is server.js. This will set up our server. And it will basically route to the appropriate middleware and controller, or routes, right? So we have our routes, but what it does is it determines when do we access our middleware, and then when do we access our routes, right? So basically it'll say, a lot of times it'll say, first things first, when we receive a request, send it to our middleware. For example, send it to our auth middleware.js file, which will authenticate the request. Then after passing it through the middleware, what it'll say is it'll say, following that, send it to the appropriate route if it's authenticated. And so then it'll go to our route. What the routes are is the specific location of where our resources and our code should be held. So in this case, once our middleware has been authenticated, once our user's been authenticated, we'll send it maybe to a user routes, which is going to maybe try to access a user from a database. Now, using this routes, we're going to trigger our controller, which handles all of the logic for our routes. The route is just basically a structure that gives us saying, hey, this is a specific endpoint for our data. But then this is the logic which will then try to access our database. And so this might maybe call an API that's external to access a database. So this backend logic will go ahead and try to access the database. It'll return data, and we will parse according to our models, which is basically how our data is structured. So these database models are important because they break down our data into a way that we understand how it's structured. And then that database model, or that user model, will then get returned as a response back up through our route, through our middleware, and then back out through our server. Some other utilities and things like that could be stored in utils, for example, a logger function. And then we have our configs, which is our configuration for maybe our databases, our servers, etc. Another directory we have under our main directory is tests. This is for unit testing. And then we have our package.json, which is our Node.js package. We have our .env, which is our environment variables. This is typically where we hold our secure data, such as API keys, etc. And then we have gitignore, that's a git file, and we have readme, which is our documentation. So this is how you would structure an API when you're coding it. Again, this is very important information. So if you haven't taken note of this, if you want to go back and look at the video later, this will get posted up, this video as well. So now bringing this back to our architecture, we have our serverless orchestration here. And what we can do is we can create a serverless API using our gateway here, which allows us to route to specific endpoints, and our endpoints will all be stored in our gateway. And what we'll do is when we try to access an endpoint, we will set up our gateway in a way that maybe it will send a request to a function which will authenticate the user. And we can do that all with built-in cloud-provided functions, right? And then maybe we'll get passed to another function which will go and retrieve the assets. And then all of that will get passed back up to the gateway. So a serverless structure is really great when you're trying to implement an API because the cloud provider provides all of the structure for defining the rules of the API. And then what it does is it allows you to create one without having to code it yourself and define the structure for your API and then access internal cloud functions and services with that API. So some benefits of a serverless API architecture are scalability. It's very scalable because, again, everything's containerized and scaled. It's very cost efficient because with serverless architecture, you pay for the resources you use, not for the actual idle time of that code sitting idly on your cloud infrastructure. And then you have reduced infrastructure management. Usually the cloud provider manages most of it. And then that includes a faster time to market. Do y'all have any questions? I believe this is the last, yeah. So that's the last bit about our lesson today about APIs. I kind of ran through a lot today, but we did have more of a limited time with a lot to cover. I feel like it was a pretty successful lesson, but if you need help, please review these lessons. Please reach out to me. If you have any questions, feel free to ask me now. Please bear with me today. I woke up at 1 a.m. this morning to get on a flight from Mexico at 6 a.m. back to San Antonio. Then my mom drove me up to Austin. I had to do class, which I teach part-time. And so it's been a long day. But if If y'all have any questions, speak up now. And if not, please go ahead and fill out your attendance for today. Again, attendance has been lacking a little bit, but I appreciate y'all for showing up, and I'll be checking in with everybody who hasn't been, just to see if they still want to participate and if they need help with anything.
Andres.
Yeah, what's up?
Hey, so I've never really looked at the containerization of, so like you were saying, going serverless and then having a container for the AI. So are you talking more specifically? Can you do that with the AI, like the API, OpenAI API, or are you talking about more with having your own LLM?
So essentially, it depends on how you're actually deploying stuff. If you're working with LLMs, you could already just have access to an LLM through an API, right? So that way you
Yeah.
just send your request in and then it returns the response, and that's most likely what you're going to do. But if you were building out your own LLM, you would basically host it in a containerized format, most likely, and then deploy that onto maybe cloud infrastructure that you can access through like API gateway. So that was more what I was referring to, but that was just where my brain was heading. But most likely in your case, to streamline things, you'll be subscribing to an LLM service and having an API key to be able to access that LLM at a fixed rate, right?
Yeah, that's exactly it. And the thought is to maybe do the containerization later on.
Yeah. And I really wanted to talk about AI today because LLMs do fit into the whole API workflow. However, we didn't get to it. I think that might be a next week's topic when we're talking about data because it is largely data heavy. And we'll be talking about accessing external data resources next week.
Yeah, that would be awesome. That was something I was, for another project, I was thinking about how to manage it and running it. I was kind of on the fence versus like running it locally or using a service or like containerizing it.
Yeah.
So that would be awesome to kind of go through that next next week.
I think what I'm going to send out this week as a take-home video is how to develop a serverless API, because I think I want everybody to capitalize on developing APIs serverlessly instead of with code. And the reason being is that they're a little bit more efficient, and you can access all of your cloud content without actually having to mess with it too much, uh, without having to code everything in yourself, right?
Yeah. I mean, it sounds. I definitely. I've never looked at that before. I'd like to see that. Sounds interesting too. The dashboard. But what was I going to say? Oh yeah, you were mentioning about the. I think you said security wise. Did you say so? Like security wise, which one is better? And yeah, I guess could you just go into detail on that?
I recommend serverless, uh, especially if you're a beginner. And the reason being is that AWS and other cloud platforms give really robust security features, such as role based access, which means that only certain roles can access certain parts of the server. So you really define exactly, you have to literally define security policies which say you can access this or you cannot access this. Um, so it's very deliberate. And I like that a lot versus if you are creating an API on your own and deploying it on your own, you are in charge of all the security features, and it's really easy to overlook something important. So it's a learning curve. AWS is a huge ecosystem, but we're going to talk about it in a future lecture. Right now, we're just trying to jump into it. So what I'm going to do is, I think uh, this will be this take home video is going to be on API Gateway, but like next week's we'll have one on like DynamoDB or maybe MongoDB, right? So that's the goal there.
Awesome.
Yeah. Okay.
Just want to
Oh,
is the server more efficient? I mean, not more efficient, more costs, cost economic.
doing the
Sorry.
back end front end.
Sorry, I was getting the call. Yeah, so is the serverless approach? It seems more secure. It seems like it's more efficient. Is it more costly or no?
It's more cost effective actually because the serverless means that running a serverless program means that your code is only triggered whenever it is needed versus if you're running a backend as a container on AWS, that container basically exists and runs idly until somebody tries to access it. So it's much more cost effective to have a serverless application. The issue is having a serverless application limits the amount of logic you can have in the back end. So if you need something that's going to be super heavy, like maybe running your own LLM, that would be a containerized solution versus having something where you're just using somebody else's LLM and you're triggering some backend logic using serverless functions. Super cheap, super cost effective, way better than containerizing everything yourself.
Mm-hmm.
So
Okay.
for y'all's purposes, I think for everybody's purposes in this program, having a serverless model is going to be more cost effective and better overall.
Okay.
But
Thank you.
yeah, of course. So I would like to open up the floor to any other questions. Anybody else? If there's no questions, let's start with Josh and Ion first. How are you feeling about the project? How's it going? What are y'all working on? Anything that I can help with?
Can you hear me?
Yeah.
All right. Yeah, we're doing pretty well. We all took a little break over Thanksgiving, but yeah, we're pretty much connecting the front and back end, testing out the OpenAI API, and yeah, we have like the database set up. We're pretty much testing everything out, and still working on the UI. And once we have the UI set up, we'll pretty much take that React and then convert it to React Native.
That's sweet. Okay, that's great. Yeah, let me know if you have any questions. I feel like everybody on your team has a pretty good, like, they can wrap their head around it. Everybody's very, like, active on your team. So, way to go, y'all. I appreciate y'all a lot. Anybody on the Ion team have any questions, input, anything? Okay, sweet. If y'all have any questions, feel free to reach out. But all good there. Let's move on to who else do we have here with their own project? We have Jeff. How's your project going?
Hi, Andreas. Yeah, sorry to tell you, still consumed by work, so I haven't really made much progress. This week should be my last work week. I don't. How many more weeks do we have?
We have, I think, I think this is only 7 out of like 13. So I think we have like 6 more. So we have a solid.
Wow. So is this going to go through January next year? Obviously.
Yeah, it goes till January, I think 21st, I want to say. But we do have 2 weeks off for Christmas break and New Year's. So we'll have 2 weeks off there, which is going to be kind of a nice chill week. Much needed. But do what you can. The goal is just that you get to practice, right? And we would prefer that you come out with an application and a project already ready to go, but since you've been limited on time, you are pretty behind, and it would be a lot to rush into. But if you need any help figuring anything out, just let me know. I'm always happy to help.
Sure, I'll contact you on Discord.
Okay, sounds good. Any questions for me or anything?
None.
Okay, sweet. Well, I hope you have a good week, and feel free to touch base anytime. Alex, how is your project going? Alex, are you there? It is possible that he is momentarily out. But if y'all don't have any other questions or comments for me, oh, hey.
Yeah, sorry about that. The app was messing up.
You're good. How's your project going?
Honestly, I'm in a similar position. I haven't gotten very far with it. Truth be told, I did want to, or I was wondering if you happen to have any availability either Thursday or Friday.
Yeah.
Those are the days that I am off, but I would like to, excuse me, have some time to talk more about it with you and just general questions. But yeah, there's just been a few chaotic events that happened in life so far. So
you're good. It does happen. So I'm most free on Thursdays. Tuesdays and Thursdays seem to be the days for me. So
okay.
Send me whenever you want to meet on Thursday. I think my calendar is pretty much wide open. So whatever works best for you. But yeah,
sounds
I'm
good.
More than happy to answer any questions you got. And yeah, if there's anything that you think the whole program might, like everybody might benefit from, feel free to ask now. But if you need more time to think, you can bring them later, etc.
Sure. Yeah, I guess mine's a little more. They're more specific, but
okay, sweet. Well, I'm happy to help. Just let me know when you're free on Thursday, and I'd be more than happy to jump on the call.
Sure thing. Thank you.
Yeah, of course.
Andreas.
Yeah.
What days did you say work best for you?
Tuesdays and Thursdays typically.
Okay, cool.
Yeah, those are pretty flexible days for me. So if y'all need help on those days, just give me a couple hours prior notice, because sometimes I do frequently put my meetings on those days, but I'd be happy to hop on a call with y'all. But yeah. Awesome. If y'all have any other questions, feel free to speak now or forever hold your peace. If not, we shall be dismissed and I shall go to sleep. I really appreciate y'all showing up today. I feel like I got out what I wanted to teach today, so I'm really happy about that. Yeah, of course, Ruth. I will see y'all next week.
Sounds good. Good night.
Have a good night.
Thank you. Bye.
Bye. Desconectado. Cool. All right.